Okay, hi everyone. So today will be the next video for PF Tuition, the H2 Math video. So today's video will be on integration. For the JC1, you should be starting soon or should have started already. For the JC2, this is a very important video for you. So please watch until the end. Okay, so the integration itself is something that you have learned since Sec 4 when you're doing additional math. And when you first learn it, actually the key idea was it is the reverse of differentiation. Okay, just go backward. So you differentiate, you get A from B. All they're asking you to do, can you go from B to A? Okay, so and this is a very important topic for engineers because calculus, talking about rate of change, is almost a daily affair. I mean, in the past, when I was looking at some of my friends who are doing engineering, they are actually looking at this thing whenever they are doing calculations and trying to figure out what's what. Yeah. So this is really a very important topic. And as an engineering student in the past as well, okay, I also get to see a lot more complicated integrations that I got to do. Okay, but of course, back to basic is yes, it's really just about going backward. It's about going backward. And of course, in mathematics, especially at JC, complicated expression is expected. But I would say that you as a student or the person doing the question, right, it's your responsibility to simplify the expression as far as possible as you go along. So never leave very complicated expression as it is and then continue to do it, whether it's differentiation or integration or just simple algebra. So make it a habit to simplify first before you move forward. And definitely it will help you in complicated questions like this, like integration and differentiation. So starting with the basic, today I will focus on the rational function, which is the one that has fractions. Okay, and this is the one that's very commonly misunderstood or you have problem understanding what to do because there are so many different forms or so many different ways you can actually do the problem. So like for instance, if you look at this very first page here, inverse trigo, something that you learn only in JC. So inverse trigonometry will involve you integrating a fraction that has a square root at the bottom. So if that's the case, then you are looking at the inverse trigo for sine. So if you integrate this, you will get your sine inverse. On the other hand, if let's say you talk about tangent, tangent is the one quite uniquely from sine, that there's no square root. And usually you will be able to put it in the form of a squared plus x squared. And then if you integrate it, you will get a tangent inverse. Basically, just need to remember, if I differentiate tangent inverse, I get the 1 over 1 plus 10 x squared functions. Okay, and the confusion will be here because in the case of inverse trigo, most of the time, right, you will be getting an expression with just number at the numerator of the fraction. So if that's the case, then it is almost 99% of the time the inverse trigo kind of question, especially if you see a square root. And inside the square root, also take note that the square root has two terms whereby there's a constant minus away the x squared term or some x term. So then this is likely going to be a inverse trigo problem. The thing is that when you're dealing with integration question, you need to have a good sense of things and you need to do it very systematically, especially for a question like that. Because you look at the fractions, the thing is that there could be different form. So what comes to your mind and what are the things that we decide criteria? So it's like a flow chart. If it's this, then it's A. If it's not, then it's B. That kind of thing. So it's a primary school kind of flow chart. So you need to have the kind of decision flow chart as well, mentally in your brain. And of course, at the bottom, there's also two formulae that you learn in JC. The one that got to do with f prime bracket fx to the power n. So this one, I will at this point bring out to you that this one, the n, right, quite commonly it is the problem whenever you are dealing with half or negative half, square root or the square root at the bottom. So whenever you get square root at the bottom, if it's not sine inverse, then you might want to consider this. So this one is of course especially the case, right, where the numerator looks like the denominator's differential, the differential, which is the f prime. Okay, later we will look at some question like that. And of course, the other one, the one at the bottom, right, the f prime over fx, this is only the case where the denominator has a bracket that is power 1. So for example, right, if let's say you have 3x over, let's say we have x squared plus 1, for example, like that. So if we were to differentiate the denominator, you will get 2x plus, okay, no more plus, it's just 2x. It will just be 2x. Okay, then this could then be the differential, okay, the top will be the differential of the bottom. So you differentiate the bottom to see what's going on. And just like I mentioned, right, you use this when the bottom has a bracket that is power 1. So in fact, x squared plus 1 is similar to a bracket of power 1, so that we can just remove the bracket. Okay, then you should be using the last formulae. Okay, so I'm just briefly going through some of the things to look out for, like inverse trigo, normally is the square root at the bottom, or the bottom part can be expressed in the form of a squared plus x squared. Then the other two formulae will be the first one, the one with the n plus 1, right? The fn1 is usually involving a square root or a negative square root, something like that. But of course, there are some more characteristics that we need to go through before you can decide which one is which one. Okay, but this is a summary of some of the formulae that you can get confused over and what are the characteristics to look out for. So apart from that, the other one that you probably will need to know how to do is this thing called the integration by parts. I always tell my students, if let's say all else fail, doesn't look like any of the formula that you learned, it is likely going to be a integration by parts. This is the last resort. Okay, don't talk about the case where you talk about integration by substitution. That one is a very specific action or instruction in the question to ask you to do it. But integration by part usually is the question will not ask you, but you have to realize that yes, okay, I need to do integration by part. So most of the time when you find that the integration cannot be done directly, it is likely, okay, I won't say 100%, integration by part. So in the integration by part, right, you need to be able to figure out which part is the part that you differentiate, which is the part that you integrate. Okay, and always integrate first. So this part is to show you that integrate the part that you want to integrate first. So I will say integrate first, okay, differentiate later. Okay, remember this rule, integrate first, differentiate later, and always subtract. Okay, always subtract. Okay, remember that, always subtract. So integrate first, differentiate later, and number 3 is always subtract. Okay, always subtract. Okay, and I have one example here. Imagine you have a ln x. So once again, if you think through all the things that you learn about integration, right, you will realize that, cannot integrate ln x. Yeah, cannot integrate ln x. So which means to say that it's not integrate, you can't integrate directly. But in actual fact, this is hidden in the question, that this is really just ln integrate of 1 multiplied by ln x dx. So this one is something like a reverse of the product rule. You're going backward, that you must always have two things. So if it's just ln x, that means to say the other thing must be a 1. Okay, must be a 1. So 1 times ln x. Okay, then obviously when you do this, right, you will have to, in this case, integrate the 1, differentiate the ln x. Let's put it this way. While in school, you might have learned something called the Liak rule, but I always tell my students, think about this. You want to integrate this. Question is, number 1, I don't think I can integrate ln. Okay, so which also means to say that then you must think of something else. And to decide which one to integrate, which one to differentiate, right, I will say that at the end of the day, the second thing that is on the right side that you're going to subtract later must be simpler to the point that you can integrate next. Okay, so this is a golden rule. If you choose wrongly, you will find that in the next integral that you're going to do, it will become harder to do. Okay, so you mark my word, this is definitely correct. So if you continue from here, okay, notice that this is actually the result. So I integrated 1, which become an x. So x times ln x, you put it down. Okay, don't do anything already. Then you subtract. Okay, subtract. Put down whatever that you have integrated. So this one is being transferred here. Notice. Then go on and differentiate your ln x to get 1 over x. Then after you have done that, x times 1 over x is 1. Then can you see that, now I can integrate. I can integrate 1. So that means to say you have done the right thing. So you might not necessarily need to remember your Liak way of remembering which one to differentiate, which one to integrate, but you will know you are right when you have done the right thing, because in the next integral, it can be integrated. So from here, I continue the simplification. I will get x dot ln x minus x plus c. Okay, so this is what you can do for integration by parts. Okay, coming to the next part. So now talking about those that have a mixture of techniques. In essence, I will say that if let's say you want to know which method to do, right, you can try to follow this. You can come up with your own also, but this version is one of the things that helped me to work out more difficult problem. So rule number one will be, right, I will check if the numerator has an x term in x, because this is the most complicated. It could be f prime over fx, it could be f prime fn, so it could be both. But I see whether there's an x term inside. Okay, if no x term, then everything is easier. Okay, so if no x term, right, then I'll see a denominator. Can factorize? Then if can factorize, then you do a partial fraction. Okay, if cannot, then you check, can I complete the square? Then it will become a inverse trigo. So if can factorize, this is a PF question. Then you integrate, you will get ln. Okay, then if let's say cannot, then I will say complete the square, you will get inverse trigo. Okay, so things like this. I would do all this to help me to check. But if let's say quite clear that there is an x term, then x term could also be inverse trigo, because maybe f prime over square root of a square minus fx bracket square. Could be that. Or maybe all you need to do is that, right, you want to see to differentiate the denominator, see whether the numerator is the f prime of the denominator. So maybe we can use one of the formulae at the bottom where, like this part. Maybe we can use this. Could be this too. Yeah. So if I were you, if let's say there's x term on top, this is what I will check as well. Okay, of course, by just going through this will not help you. We still need to go through some question. So let's look at this very first one. So x plus 1 over x squared plus 2x plus 4. Okay, then the first thing that comes to my mind will be, okay, there's x term at the top, there's x term at the bottom. Could the x term at the top be a differential of the x term at the bottom? So let's try. If I were to differentiate x squared plus 2x plus 4, what I will get is 2x plus 2. Okay, look very similar to my numerator. So what is lacking in the numerator is a 2, right? So what we can do in integration is that I multiply a half outside. You cannot change the question, but I can always add things, right, if I were to do the reverse outside. So that's the beauty of integration. Then from here you can see that 2x plus 2 is the f prime. Then the bottom is the fx. So according to the formula that we saw earlier, this will be half ln x squared plus 2x plus 4. Okay, then plus c. Remember for ln, okay, for ln, you have to make sure you put a modulus now, because the things inside cannot be negative. Okay, so this is example problem number 1, just like that. Okay, so identify that the numerator could be a differential of denominator. So I differentiate the denominator first and I see what I get. So and then I realize that, oh, okay, the difference is only a 2. So I multiply a 2 to it, then I times a half outside, so I'm not changing the number. Okay, so this is example 1. Example 2, 8t cubed over square root 2t4 minus 1. Just now I did say that this could be maybe inverse trigo of sine, but actually no. Okay, this is not inverse trigo. So there are a few telltale signs to tell you there is no. First of all, right, if it's inverse trigo, you notice that the thing you should be integrating, right, should be like this. Let's say for sine, you will notice that the x squared is at the bottom, sorry, is at the back, not in front. So in this case, the t4 is in front. Although I can t squared bracket square, but the t4 is in front, should be at the back. So this might not be inverse trigo. Then the next thing I will check will be, could this be the formula that we have learned? So once again, I will take the 2t4 minus 1, I try to differentiate it. Then what do I get? I will get 8t cubed. Isn't that my numerator? Yeah. So in actual fact, this is once again the formulae. So from here, then I will continue. Okay, but the formulae is the one for f prime over fx. This one got a square root. So if there's a square root, actually do not fret, don't worry. Okay, this is actually still doable. So you just put a bracket, put 2t4 minus 1, the whole thing to the power of minus half dt. Okay, so this is f prime fn. Okay, the n is minus half. So now I just need to continue. It will get you 2t4 minus 1 raised to the power of half, then divided by half. So you basically got to reverse everything. So when you differentiate, the half comes down, multiply by half. When you reverse, you divide by half. And then plus c. So the final answer will be 2 bracket 2t4 minus 1 to the power of half plus c. Okay, let's check. Yeah, that's the answer. So example problem 2. So you might be thinking, hey, how come it's like so easy to me? Maybe for you watching the video, right, you have to think a while. But I don't seem to need to think. Okay, it's because that I have a very systematic way of checking. So I already know what to expect. Okay, last one. Okay, last one, you can see that e2x sine x. So the question is, wow, I never done product of term before to integrate that. Okay, there doesn't seem to be something that I can do immediately. Which also means to say that this is none other than the famous integration by parts. Okay, so there's two terms. This is the u, this is your v. Okay, so in formulae wise, they give you the u and v to help you understand that one part you have to do integration, one part you have to do differentiation. But to me, I don't really go to that. I will just remember that if I have done this integration or differentiation, after I do it, it should be easier, so in the next part I will be able to integrate. So keep that in mind. Okay, let's say we integrate e2x and we differentiate sine x. Let's see what we will get. So by parts. So after integrating e2x, I will get e2x, and then there's a half here. So because the power has a 2, so the reverse of it will be times 2 become divided by 2. Okay, then we have the sine x, don't do anything to it, minus away the integration of half e2x. Okay, then differentiate sine x, you will get cosine x. Okay, so this is what you will get. Then you will see that you are stuck. How do you continue from here? Okay, so this is one of the rare questions where you have to look at this entire thing as an equation. So in fact, in the next line, I will write the question in front first. A bit no space already. So the actual question is like that, right? So later on you will see what I meant by you have to take this like an equation. Okay, something like that. So the original question, right, you still write down. You will need that later. Okay, how do we continue from here? There's no other way you can do this but to integrate one more time. So let's continue. So integrate e to x sine x dx, right? This one will become half e to x sine x minus half, then put a bracket. So we do the same thing. Half e to x cosine x, and we will have to subtract away integration of half put outside, e to x sine x dx. Okay, notice that the question came out again. Yeah, it's for that purpose. So after it come out again, the next thing or the last thing you need to do to find the answer is that bring it to the left side. Now I can combine. So if I were to expand this, right, minus half times minus half, I will get a total of plus 1/4. I bring it to the other side, it will become minus 1/4. So the final answer looks like this. Okay, 1 minus 1/4 will become 3/4. I skip some step. Then this will be equals to half e to x sine x minus away 1/4 e to x cosine x. Alright, something like that. Last but not least, divide by 3/4 on both sides, and the final answer will be the integration of e to x sine x dx is actually okay, 3/4 you divide by 3/4 will become flip over times 4/3. So 4/3 times half, you will get 2/3 e to x sine x minus away, okay, just 3e to x cosine x. This is your final answer. I have deliberately chosen this question because it doesn't only show you integration by part, but at the same time to show you that it is possible for the integration by part to not work. Actually, it's not to say not work, but just that you will not be able to get a different expression, because when you integrate exponential term, you get the same thing. You differentiate sine, it will just cycle between sine, cosine, sine, cosine, sine, cosine. So there's no way to get rid of it 100%. And as a result, right, you must look at this question as a whole, that the question itself is part of the equation that we can make and bring to make the subject, then eventually you will get the answer. Okay, so that is the last example problem for today. I hope this gives you a good start point for your integration topic, because these things that I talk about here will be the things that you continue to struggle throughout the 2 years. And if you sort it out now, then you will find that in the future, it will be easier for you to tackle integration problem. And maybe one last thing to remind everyone, the only thing that you will struggle in differentiation and integration, to be honest, my opinion is that it is your techniques. Okay, don't tell a teacher that, oh, I don't know how to do the application question for differentiation, I don't know how to do the integration application. Not really that. The main thing that you need to sort out is your techniques. Your differentiation, your integration, are you familiar with the rule? Do you know what to do? Do you know how to manipulate? So these are the things that you need to figure out first before you can do the application. So when you are struggling with integration or differentiation, what you are really struggling with is the techniques. Okay, it is not really the question itself yet. Okay, because you're going to apply the techniques to those questions. You cannot do those techniques, you cannot do the question. Okay, anyway, that will be the last point that I want to make. And thank you for staying throughout for the video. Okay, if you like the video, please help me to share and subscribe to my channel. And of course, in the next video that I'm going to shoot, I'll talk about more of the application of calculus, so to help you to overcome the upcoming promos or your A-level. Okay, thank you very much. I'll see you again in the next video.